Testing, testing. 1, 2, 3. 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 Trying to make sure my clicks aren't too loud. But they seem pretty loud. The demo gods will not be in my favor. Absolutely not. Not when I set this up last night at 3 a.m. And then worked on this an hour today. So. So the demo gods actually aren't in my favor, actually, because I just tried to VPN to Clemson and it just wasn't working. So I'm just going to be running the binaries locally, but they are hosted there, so deliberately turned it quieter because of the absolute mashing that is my keyboard. Otherwise, you're gonna get something like. More click equals more hacker. If only. Be flying on the keyboard. Oh, I'm live. Oh, sweet. Nice. Maybe if Max was actually in the... Maybe if I could hear the voice channel? Why do I feel like I can't hear the Discord voice channel? That might be concerning. Hear the voice channel? Interesting. I see Max's mic moving, and yet no audio.
Can you hear me?
Yeah. It might be seriously delayed. But I literally couldn't hear Max at all. So. What? Oh, yeah. I gotta turn desktop audio off. That's why. Okay, go. Sure. Alright. So, welcome. Welcome to Binary Exploitation. Let's get this thing on the road. So, in short, it's essentially exploiting binaries. So to start on that, we're going to need to do a quick C recap. For all of the freshmen in the room, I don't even know how many there are, but for all the freshmen in the room, by this point, you should have some familiarity with C, enough to actually understand this presentation. So for Hello World, everyone has seen this. I know you have, if you've gone through a C course. There's not much going on here, but you have your main function, and we're just going to be printing a string for Hello World. It's dead simple. And so now what we're going to do is we're going to expand off of this and just introduce a couple more C concepts that we can actually use to exploit some binaries. So the first game we want to play revolves around memory and C. So at the end of the day, binary exploitation really comes down to abusing memory objects that exist within a binary. So whether that's a buffer on the stack, or an integer, or even heap allocated or dynamically allocated memory, that's essentially what you're going to be exploiting. Some exploits get a little bit even more advanced, where they're exploiting the layout of the compiled code itself. So when you compile this hello world binary, what you actually get is one of these elf executables. So if I run the file command, it'll say it's a 64-bit elf executable, and it is position independent. We'll get into that in a minute. But it is compiled code. It's no longer your source code, and you can exploit how the compiler compiles the code and abuse data structures inside that. So let's play a quick game: stack, heap, or static. So in line with the whole exploiting data structures, let's just take a quick game on what is the stack, or what is in the stack, what is in the heap, and what is static. So we have a very small program here, and you can try and take some guesses now ahead of time, but I'm going to go ahead and walk through the differences between each three and then sum it all up for this program. What is stack, what is heap, and what is static? So stack variables are variables that are allocated and freed automatically. When you create a stack variable, you don't have to do anything to manage the memory behind that variable. The stack is not limitless. Most have an upper bound. So the question I would pose to you guys is, what is it called when you exceed the memory limits of the stack? And of course I can't hear you, but what you should be saying is Stack Overflow. So your favorite programming website, that's where it comes from. It's a Stack Overflow. When you say allocate 5 million integers on the stack can't necessarily store that space, and so you get an exception raised called Stack Overflow. The stack grows and shrinks as variables are created and destroyed. So a quick example of that. If we look into our program, we can see this foo function. This isn't an accurate representation. This is actually what this looks like as far as this integer being declared. So we can see here that there's some assembly instructions going on, but what's happening is that we're subtracting the value 4 from RBP, or it's just a register, but we're subtracting 4 spaces of memory off of the stack to create space for this integer. So that's how the stack is managed, and all of that code gets generated automatically for you, so you don't have to manage any of that. And at the end of a function, stack variables are destroyed. So stack variables only exist when the function that created them exists. So if I call foo from main, that bar variable is going to get stack space allocated for it, and then when it returns, that stack space is going to be destroyed in essence. Now nothing actually happens to it, it just moves a pointer around, but you can't necessarily access that variable from main, right? So if I tried to call foo and then print bar, right, I can't do that because that variable doesn't exist in the scope of main. So that's just not going to work. Now on to heap. The heap is managed by the programmer, so this is something you have to keep careful track of. You can do this through, you can create and destroy heap variables or heap memory using malloc and its friends and free. So malloc, calloc, realloc can all create heap memory, and free can free it up. So the heap is very large, and it's usually limited by the physical memory available. You can allocate a massive amount of heap space, and you're still going to be okay, whereas the stack, you'd run out pretty quick. And the heap requires pointers to access it. So lastly, we have static variables. Static memory persists throughout the entire life of the program, and is usually used to store things like global variables or variables created with the static clause. So all you have to remember there is global variables and static variables, so variables that literally say static in front of them. So now going through this program, we can identify what is on the stack, what is on the heap, and what is static. So starting with the stack, we can identify that this bar variable is on the stack. You saw it in the object dump that it was being made space on the stack for it. For heap, recall that malloc, calloc, and realloc all create heap memory or allocate heap memory. So we have memory being placed, or a pointer to that memory being created. And then we finally have it being freed by free. So this has to deal with heap. This has to deal with the stack. And then up top here, we have a global variable and we have a statically defined variable. And those are both going to be static. So now let's talk a little bit about binary security. So when you compile code, these measures are going to be put in place for you. You can opt to turn them off, but it's not recommended at all if you want your binaries to be secure. So when you're compiling your C code, it's going to do a lot of things for you. For example, I compiled this stack heap static binary, and it gave me this 64-bit LSB executable with Pi enabled. One thing we can use to check the binary security or check our binary security is using this checksec command. It's not found on every distribution. You can just go look it up online. But it can tell me that NX is enabled, Pi is enabled, and all that's enabled. So let's get into what those symbols actually mean. So first off, the stack canary, you'll see here that my stack heap static didn't have any stack canary. So what is a stack canary? A stack canary is just a random integer that's placed before every return pointer. And what this does is it prevents machine code from being executed after a buffer overflow. You're going to hear buffer overflow talked about a lot throughout this presentation. We also have 3 examples for a demo that goes over 3 different levels of a buffer overflow. Essentially, buffer overflow is just writing past a buffer. So in our function above here, we had this char baz 32, and now if I were to do like a memset, and then I like filled some data in it, and then I returned. Well, a stack canary would be placed. Ideally, it doesn't just knock it out or pre-optimize it. But a stack canary should be placed into the binary now that I have this buffer that's placed on the stack. So you can see here it says canary found. And so all that's going to do is if there were a buffer overflow to occur, or if a buffer overflow occurred, the stack canary would be overwritten and then code couldn't be executed. So whenever you declare a buffer like this, you're going to have a stack canary present in your program. You could also alternatively delete that or not include it rather. So if I did stack heap static and then I did that to compile and then I did fno stack protector and then I checked it again, now I just removed my canary from being in the program in the first place. So if you want secure code, do not compile with fno stack protector, but if you want to play around with binary exploitation, that might be a good flag that you want to look into. NX, so you see how it says NX enabled here. So NX is the no execute or non-executable bit. This prevents machine code from being run on the stack. So this is again another buffer overflow protection mechanism. So a long time ago, buffer overflows were running rampant in the security community. There's a really old frac article called Smashing the Stack for Fun and Profit by Alif1, and since then buffer overflows have really run the course. So many programmers weren't checking for these because they just didn't really know it existed. A lot of programmers today still aren't very security minded, so you get a problem there. But so these variety of protections have been implemented, including stack canaries and now NX, so the non-executable bit, and it just prevents shellcode from being run on the stack. So you can see here the NX bit is enabled. So if I were to place shellcode or machine code or instructions onto my stack variable like baz, it wouldn't actually execute. It would seg fault. Or not necessarily seg fault, but it would raise an exception. So pi is also another binary protection. This isn't necessarily against buffer overflows, but it does help in regards to any kind of exploit because it just makes things harder. So why does it make it harder? Well, it randomizes the binary's base address. So what does that actually mean? Well, if I were to go into GDB, and I know this might scare some people, GDB is scary, and I want to break on main. Well, we saw here that I set a breakpoint on main, which was at the address 1185, hex 1185. But when I ran the program, it's actually at 55555.185. So the binary's base address would normally be at that, or in the case of 64-bit 64-bit binaries, it would be at 400,000. I think I can do no pi. And then run it again. Yeah, so now you see it's at 400,000 plus 1185. So what that value could have been. Now if we run, it's still that. Whereas with the pi binary, you are getting addresses in a random range that's really high. So if somebody wanted to do some binary exploitation, they couldn't rely on knowing the exact address of where something is within the binary, right? For here, you know exactly where main is, but up here, you don't necessarily know where it is. It could be at any random address. You'd have a hard time locating it. So that's what pi does, is it randomizes the binary's base address. You can see this with VMMap. So if we were to look for the binary's base address, it would be right here where the top of this very first line is. So at 400,000, my binary stack heap static is mapped here. So onto ASLR. So ASLR stands for address space layout randomization. What that does is it randomizes the stack heap and library addresses. So if we go back in here, we break on main again, and we run. So the addresses are very high. So 7F, blah, 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 blah. They're very high addresses. And so you can see where the stack is here, and the heap hasn't been initialized yet. So if we just, if we were to break on a section of main, say after the malloc call, say before free and after malloc, we'll have a stack trace here, or stack output, but we should also have some heap, though I'm not seeing it. But ideally, you'd have some sort of heap address range, and so instead of saying stack there, it would say heap, and then you could see the base address for that. So ASLR randomizes the stack, heap, and library addresses. You might have seen libc loaded there. So when your program calls functions like printf, the libraries such as libc have to be loaded into your program's address space so that they can call that function, because you didn't define printf. Printf is defined by the library, and so it needs to know where to go in order to execute that library function. Now on to some exploits. We covered the defense mechanisms. How can we get around that? So the first exploit we're going to talk about is an integer overflow. So an integer overflow looks a little bit like this. So take a minute to yourself and think about what these two values will end up printing. I'll give you a hint. The initial value will still print 127. But what would happen if we were to add 1? So integer overflows abuse how computers represent integers in memory to wrap an integer into the negatives. It's another pretty big hint. What do you think the add 1 line will print? Let's take a minute. And if you guessed negative 128, you would be correct. So what is essentially happening is you can see the bits laid out here. So our 127 value will have the first 7 bits as 1s, and then the 8th bit as a 0. But what happens is when you set that 8th bit to a 0 and all the other ones are zeros, that bit signifies that the number is negative. And so since it's a negative number, but it doesn't have any of these, it's going to wrap all the way around to the most negative value that this integer can hold. So that's how they can represent from negative 128 to 127 values. Now, if you were to have something like uint 8t instead, that would go from, so these range from 0 to 255. So they both hold the same number of values, but this one holds a different range, right? So the integer held from negative 128 to 127, which is 256 values. But this one holds from 0 to 255, which is still 256 values. So what happens when we set that to 255 and then we add one? Take a second. If you guessed 0, you would be correct. So it wraps right back around, and it becomes 0. So now we're going to talk, well, in math, essentially, right, you have 1 plus 1 plus 1, and that approaches infinity. But for a single integer on a computer, its data is bounded by the size of the data that one register, or in our case, a data type, can hold. So obviously you can't hold the value 1 million in an 8-bit integer because you just can't represent that number. It's just not possible. So the values are bounded by your data size, your data type size, or by the data you can fit in one register. Now on to the main course, buffer overflow. So a buffer overflow abuses a C-style buffer to overwrite a value or values stored in memory. And this is perfect when there are no binary protections in place. Now you can execute buffer overflows when there are binary protections in place, but typically you have to work around them using some means of another exploit. For example, format string. We're going to talk about that in a bit too. So here's an example of two different functions that both utilize buffers that are on the stack, and they both call fgets. So you have two buffers on the stack. They both call fgets. One's safe, one isn't safe. Now, hopefully you should be able to tell why one is safe and why one isn't safe. So the safe one we can see here is that fgets calls, you call fgets on the buffer with size 16. And so if we look at fgets real quick, we can see, and what I did there is man fgets. Man pages are very important. Hopefully you know them by now. If not, give that a quick Google. But if we look at the manual page here, we can see fgets reads in at most one less than the size characters. So typically C buffers are gonna look something like this. So if I had a char buffer of size 2, it would have one spot here and then another spot here. And so actually should have 3 spots. So this technically you're not supposed to touch. This is the null byte here. So you can store data in the first and the second spots, but then there's going to be a null byte like that there, or just a 0, however you want to represent it. And so that's going to sit there. And so typically you're just supposed to manipulate these first 2 bytes. But if you were to write, say, some data here, and so now you have 2s all the way across, that's a buffer overflow. And so what fgets does is it reads 1 less than that size. So this buffer is going to look like this, and if we pass the number 2 to it, right, it's going to read 2 bytes. So it's not going to read 16 bytes like over the end of the null. So that's what it prevents typically if you pass in the right value. Now if we pass in the wrong value, fgets it's not really going to know how long our buffer is. So if we pass in 32 to a 16-byte buffer, you're going to have some bad times. It's going to start overwriting past the end of that buffer into data that you might not know what it is, but you could figure it out if you debug it. So if we run this, it's going to prompt me 2 times. So if I spam some A's, it actually ran 1 time because it's going to buffer wrap. But if I spam some A's, that's fine. But if I spam a lot of A's on this next one, it's going to say stack smashing detected, and it's going to abort. And so it realized, because it has a canary on it, buffer 0. So this canary is what's saying stack smashing detected. Maybe we can find it in object dump. Well, we can see here. So on the end of a function that has a buffer declared in it, so we make stack space for the buffer, and then down here you see there's the call to fgets, and then we have stack check fail, and what that function is the canary function. So the canary is stored at this segment address, so the segment register, and then it's going to check to see if it's the same value. And if it's not the same value, then it's going to call stack check fail. And stack check fail prints out that lovely error message of the program dying a horrible death. So that's an example of a buffer overflow, is we're writing too far past the buffer. And so in this case, we're hitting the canary, but if the canary wasn't there, then there'd be nothing to stop us from continuing to write past. And we could write into data that maybe we want to write into, or potentially maybe we don't want to write into. So some data that's stored after the buffer, for example, would be the return address. And so what you could do there is you could return to anywhere you want in the program. Now, if you know the location of the buffer, you can return to your buffer. And if NX is disabled, you can execute shellcode. Now, that's not a really common scenario, but it could happen. And we're going to talk about a couple more exploits that could help you do that if those protections are in place. So the next exploit will be a code reuse vulnerability. So this is an example of return-oriented programming. I'll just move this line up. Or code reuse is an attack where you take bytes of a program and you reuse that as your attack method. So we talked about NX earlier, how the stack is not executable, so you can't execute shellcode or machine instructions, or if that doesn't really make much sense to you, just think of that as more C code, right? You can arbitrarily execute C code. So with NX, you can't necessarily do that. And you need some method of bypassing that. So you still want to execute machine code to, hack the program, but you can't just execute your own. So you execute code that's already present. And this is what code reuse attacks do. And they bypass the non-executable bit. So one example, the most common, is return-oriented programming. So if we look here, and we look at the end of every function in this, you'll see there is a ret instruction, another ret, leave ret, but there's return instructions at the end of this. And what return-oriented programming does is it uses those return instructions to chain, essentially, or to form malicious code execution chains. So what somebody could do with this program is they could, assuming, you could easily exploit this program assuming there was no position-independent executable enabled or there was no ASLR. You could definitely do that. Actually, just pi here would be the main difference. But for the safe function, again, the same buffer overflow scenario, you're not writing past your buffer. This is safe, but the unsafe function you are. And so for ROP, assuming the non-executable bit was set, you could actually jump to this function. Even though it's not even called, you could execute this function with a return-oriented programming attack. And so the way that would work is you'd basically trick this return pointer into returning into that function. And then it would just execute that like any old C code. It'd be as if you called shell here. Is what would essentially happen by executing return-oriented programming attack. So running this won't really show you what would happen. So just keep that in mind, is that a shell would essentially be called if you were to exploit this appropriately. The next attack we're going to talk about is jump-oriented programming. This is significantly less common, but people thought, hey, if attackers are using return-oriented programming, why not just remove all the return instructions in my program? You can actually feasibly do that, is you can remove all return instructions in your program and just use jumps. Well, that sounded like a good idea up until the point where you realize that you can do the same thing with jump instructions as well. So you can do a similar code reuse attack using jump gadgets, though it's significantly much more difficult because you have to form what is called a dispatch table, and then you have to keep track and set things up really precisely in order to actually execute that. So while it doesn't completely stop code reuse attacks by replacing all return instructions, it does kind of elevate the bar that you need to reach in order to mount a successful attack. Last one is pure call-oriented programming. So in the same vein of those, this uses call gadgets. This I've actually never seen used. So there's a paper on it, but I don't know how it works or I don't know how effective it is in practice because I've never seen anyone actually do it. Granted, you could make a binary by hand and do it, and then you could practice that there, but as far as like real applications, I haven't seen it yet. Format strings. So this uses an incorrect call to printf to leak stack values. Forgot to make a file here, but essentially what happens is if you write a program and you do something like this, let's do fgets on the buffer. I'm writing a program backwards, but you get the idea. If you write a program that looks like this, what this can end up doing is leak stack values. So I'll call it format.c. So if I do format.c, and I do this, AAA, it prints my AAA, and that's fine. But recall that normal calls to printf, like when you're trying to print an integer, look like this. And so what this is a format string. So I can specify format strings myself, and printf will gladly take those and execute them as I like. So if I do some %x's, we now get values off the stack. And so that is no bueno. So if I run this in GDB, we can kind of get a feel for what this is actually doing in terms of leaking stack data and exposing some memory that the program is using. So if I break on main, we can see that call to fgets, this symbol main. And so I'll break on that printf call, and then we'll run it. So it's going to ask me for some data, and I'm going to give it those %x's. And we can see here, now we're about to call printf, and we're going to call it with these %x's as our format string. So it's going to interpret, it's going to interpret that. So it's instead of a, %d new line with an argument, it's just going to pass those format strings without an argument. And so we see some values here. And if I do a new line, it's going to print out 78520 blah blah blah, and so we can see that that is from there, and then it's going to print that F7. So presumably that would be one of these somewhere in here. It would end up leaking one of these addresses. I would expect it to be that, though curiously enough, it is not. I'm going to run it again with %ps instead to leak pointers, right? Because that's how you print a pointer. So I'll just do next. And those are still on the stack, so that's what it was leaking. So that would be our format string. and then that should be a pointer to something. DEF0, so that's where that is. So that's a pointer to our format string. So you can see that it's leaking stack variables, and that's essentially the basis for a format string. So what would happen if you ended up leaking the return address of this? Then you can leverage that with a buffer overflow to bypass the stack canary. You could bypass the position independent executable layout, and you can bypass ASLR as well. So leveraging a format string can be very, very useful in the context of other exploits. Heap, I'm not really going to cover this. It's extremely difficult to grasp. I'm still struggling with heap sometimes. It's just, there's a lot to it. There's so many different kinds of attacks. They're all regarded at, or they're all called house of and then something. That's like the standard heap naming heap exploitation naming scheme. You also have to think of internal heap metadata, Tcache stuff, so you can actually exploit how glibc allocates specific data structures, or like allocates memory using malloc and calloc, and how it frees memory. So common misconception is that when I create some memory, say I create some memory like via malloc, so I malloc 16 bytes. Say I malloc 16 bytes, and then I set it to A's. I set it to A's, and then I free it. Nothing actually happens to that memory. So it's marked as free, but in order for the allocator to be performant, it actually doesn't clear the memory. So common misconception is that when you call free memory, it would also like zero out the memory. So it would essentially look like that, but that's not actually what happens. So that's a common heap misconception, and you can abuse that to exploit some things. So now on for the demo. We're going to demo some buffer overflows. You can do this yourself. They are hosted on Ada3. They're actually hosted under my account. Everything's in a CH root though, so hopefully nobody ends up hacking my account. It's only a matter of time before I get banned anyways. But you can go to, if you type, I'm actually not on the VPN anymore, but if you type netcat and then the address for Ada3, alternatively ada3.computing.clemson.edu, you should be able to connect to it. Can I get some confirmation that this is actually still up? Quick confirmation. Dun, 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 dun. I think I see Willie saying that's not GDB. It actually is GDB, but I use an extension called Pwnedebug, or Pwnedebug. So Pwnedebug, well, bottom line is they teach you GDB without any extensions, and in my opinion, that's the worst way to do it. So highly recommend looking into GDB extensions, because there's just no possible way I would ever use GDB without one. It's just too painful. So yeah, would not recommend using it by itself. So here's buffer overflow 1. Oh, there's the desktop background noise. I hear Max. All right, well, there's 3 demos. I was going to walk through each of them. So can they hear me or can they not hear me? That's the real question. Hello, hello. All right. So I'm gonna walk through this. All right, I'm gonna walk through this for those that maybe don't want to try it or don't want to follow along. So this might be a little confusing. Hopefully everybody understands what a struct is. But essentially, a struct will just help us lay out things contiguously in memory. So you have a buffer, and foo is right next to it. So all that looks like is, so you have some memory on the side, and then you have the buffer, and then you have foo, and then you have some other memory. So that's all the struct is doing for us, is it's making it right next to each other. So we have the setup function. You don't really have to worry about any of that. What we're going to do is we're going to assign foo the value of 0, and then we're going to call gets on that buffer. So what that's doing, if you're not familiar with gets, we can look at it. If we see the bottom of this man page, it says never use gets because it is impossible to tell without knowing the data in advance how many characters gets will read. And because gets will continue to store characters past the end of the buffer, it is extremely dangerous to use. It has been used to break computer security. Use fgets instead. And I've shown you even using fgets doesn't make you safe, but using gets certainly doesn't make you safe. You are guaranteed to have vulnerability if you use gets. There's no way around it. So gets right here is the vulnerability, and that is what will cause a stack-based buffer overflow because this is placed on the stack. So we have printf here, and all that's going to do is going to print the value of foo in hexadecimal. And if foo is not 0, we win. So what do we actually want to happen here? What we want to do is we want to create a stack-based buffer overflow such that foo is overwritten by some value. Doesn't matter what value it is, just has to be overwritten by something. And so in order to write past this buffer, it's quite simple. All we have to do, right, is so the buffer is of size 16. So if we wrote 16 bytes, it would completely fill the buffer and write over the null byte. So that's not good, but it's not great either. It doesn't really overwrite foo. So what we could do is we can write 17 bytes. So what happens if we write 17 bytes? 1, 2, 3, 4. Just going to copy it. If we write 17 bytes, we win. So if you netcat to 8 to 3 on 4000 and you write 17 bytes, you will win. So what is that 41? Well, that 41 is the hexadecimal character for an A. So we can confirm that foo was overwritten. We can confirm that foo was overwritten with the A, the last A that we printed. And yeah, so in memory, that's what it essentially looks like. So if we write 2 A's, you see 41, 41. And so you're overwriting stack variables with a stack-based buffer overflow. So does anybody have any questions on that? You can't write, if you write 100 variables, you're going to get, if you get stack smashing detected, you've written too many variables. Remember, the stack has protection, right? It has a stack canary. So you have to write, in this case, more variables to overwrite foo, but not so, more letters to overwrite foo, but not so many that you trigger stack smashing detected. Cam! How's it going? Yes, it does. Doesn't it? All right. So is everyone ready to move on to buffer overflow 2? take that as a yes. Buffer overflow 2. All right, buffer overflow 2. So our setup function is called, and we have our struct again, but this time we have a function pointer. So does anybody know what a function pointer is? Exactly. It points to a function. A function pointer points to a function. There you go. It's dead simple right there. So what we're going to do is we're going to set our function pointer to null. We're going to print the win address, and then we're going to call gets on our buffer. So our function pointer is on the stack, and it's right after our buffer. So this is an exploit for the buffer overflow 1, by the way. Sorry to go back, but it's literally just 17 A's and you send it off. So this is using pwn tools. So I'll show you what that would look like. Right, so this is what it would look like if you were to execute it on the lab, except you would have a remote instead of process. But for buffer overflow 2, we have this function pointer. It's on the stack. It's placed right after a buffer. So recall that we have to write 16 bytes to completely override our buffer. And then we have to write data into the variable that's adjacent to it or contiguous with it. And so what we want to do is we want it to be equal to win. So our win address gets printed, and our function pointer has to be equal to it. So our function pointer is null at the start. We have to write 16 bytes to overwrite past the buffer, and then we have to write the address of win. So what does this actually look like? Well, here you go. So our win is there, and if we write, let's do an accurate amount, 1, 2, 3, 4, 1, 2, 3, 4, and then an A, our function pointer is hex 41. So we need it to be that hex number. So what can we do? Well, we can actually use echo for this. We're going to do 1, 2, 3, 4, and then we're going to pipe it in. So it's now we're just doing now we're just overwriting it the same way, but with echo. But with echo -e, we can actually pass in values that we might not be able to print. So not really sure what character hex 18 is, but potentially you might not be able to print that character. But we actually can do something like that to be able to print it. So you'll notice that hex 18 was placed after the 41. What's up? Sure. All right. So you have hex 18 over here. And so what you want to do is you want it to be the same as that. So if we delete that A, we now have the first byte of the win function. Now we need to get the second byte. So how can we do that? Well, just hex 42. That's the next one. So we go byte by byte in this order. So every 2 numbers, that's a byte. And we want to casually just walk our way up this address. So we can continue down the line. So 55, 55, 55, 56. And we end up winning. So just have to repeat that process. And now if you're getting a different address every time, you have to do it programmatically. And so one way to do that is to use pwn tools, and it's quite simple. So in our case, we're going to run this as a process. So Python 2, buffer overflow exploit. So what pwn tools is going to do is it's going to receive those 14 bytes. So this will just receive the address. So it's going to receive the 14 bytes. This will parse the address. Why are you printing the characters backwards? So There's a thing called little endian and big endian. So endianness is the keyword that you want to look up. It's spelled like this. Spelled like endianness. I believe that's how it's spelled. Like, maybe two N's, maybe one N. I don't know. But endianness is the keyword that you want to look up. So little endian is represented. So all it boils down to is how the data is represented in memory. So on little endian computers, the data is represented backwards, essentially, in memory, while for big endian, it's represented forwards. So in memory, it would be represented like this for that address. So this address is equivalent to that in memory, but on a big endian computer, you'd have it look like 56, x 55, x 55, x 55, x 42, x 18. So this is big endian, and this is little endian, and that's just how computers store data in memory. And so since we're all on little endian computers, you want to use the little endian format and represent it that specific way. If you do it this way, it's just not going to work because you're going to get what would essentially be 1842, something backwards, or yeah. So you definitely don't want to do that. But little endian is the reason why you want it reversed. So functions that can help you with this, right? So I get this 56 value, and I'm not necessarily, I want to pack it, and what that does is it translates it from this to that in Python. So that's what that P64 does, and then it just sends it off. So we have the 16 bytes as our payload. Let me scroll down a little bit. So we have our 16 bytes as our payload, and then we're going to pack that address. So we're going to translate it from this to this, and then we're going to send it off, and then interactive just returns a session like this. So that's our function pointer. It's equivalent to the win function that we expect it to be, and we win. Any other questions on that? We have one final example, and that would be buffer overflow 3. So this has a lot of crazy code at the top that you do not have to worry about. It's the same with this, same with the other ones. So for buffer overflow 3, you only have to worry about this main function, so don't worry about setup at all. The setup stuff is just to make sure that you guys can't get on my account and start rampaging through my files or whatever else. So for this, we have a buffer, and we have, we're going to print the address of the buffer. So we're going to print the pointer to the buffer, and we're going to call gets on the buffer. So this was actually compiled with a specific flag, specific flags, I should say. So the flags that were compiled, flags that this was compiled with were no stack protector. So recall that disables stack canaries, and z exec stack. So that disables the NX bit. So we're disabling NX and we're disabling stack canaries. And when those two are disabled and you have a stack-based buffer overflow, you can execute arbitrary shellcode. And so shellcode is just C programs that are compiled and the corresponding bytes, like this. So the corresponding bytes are then translated into like those hex strings. So this is something like 42 blah blah blah, that sort of thing. So these are then executed as machine code. So if you netcat to ADA 3 at port 6000, then you'll see something kind of like this. And so this is the address of our buffer. For me, it doesn't change because ASLR is disabled on my computer, but it should change on the lab. And if that's the case, you're going to have to get that and deal with this programmatically. It would be challenging at the very least to do this all with Echo, but it is possible. So if you want to try it that way, you very well could. But the idea behind this is that you're going to fill up your buffer with machine code or shell code, and then you're going to overwrite the return address to return into the buffer and execute that. So we have the address of the buffer, and main has the address of wherever it's normally going to return to. So we want to overwrite the address of wherever it's normally going to return to with the address of our buffer. And by doing that, it'll jump into our buffer and start executing code there. Because the computer is kind of dumb and it doesn't really know. It just does what it tells you to do. So one place you can get shellcode at is Shellstorm. So Shellstorm has a giant database of machine or shellcode. So we could see all these Linux x86, 64 shellcodes. And so we just kind of want to find one. I don't know. This is probably a decent one. So here is our string, and what we would do is we would, put that all together, something like that. And so you'd execute that string of machine code. But this is what our exploit looks like. I forgot where I got this shellcode from. Definitely on Shellstorm, but I'm not sure which exact one. Maybe something like this. So 4831 D2. It's kind of the same idea. Ends in FO. It actually might have been this one. So I'll just drop this in here. Drop that in there. So I just use this shellcode, and what my exploit does is I put the shellcode at the start of the buffer. I then pad it with NOPs. So NOPs are just no operation. So if a computer encounters this instruction, then it just skips over it. Nothing actually happens. So that's why it's called a no operation. It takes up space, but nothing actually happens. And so you can pad it with technically anything you want, but I did NOPs for the sake of doing NOPs. It's just standard practice. So we want to do 100 bytes because that's how big our buffer is, right? So our buffer is hex 100 rather. So we have a hex 100 byte buffer. So we have a hex 100 bytes, and then we need an extra 8 bytes of padding to overwrite or to pad between our buffer where it is and the return address. So you have something like the buffer, and then you have something here, and we'll call this junk. And then you have, so you have hex 100 bytes of there, and you have hex 8 bytes of junk, and then you have the ret pointer, which is hex 8 bytes as well. So we need some sort of shellcode here. So for my case, my shellcode was 30 bytes. So I have 30 bytes of shellcode. And then for the junk, or padding as we call it, we want whatever hex 108 is minus 30. And then we want to put our buffer address here. So wherever this value is, or however you can get that, you want to put that there. So if you do all this correctly, you'll end up with a buffer that contains a bunch of shellcode, padding at the end, and then a buffer address. And so main is going to say, okay, I'm all done with my function. I'm gonna return here. And then when it returns there, it's going to start jumping in your shellcode, and your shellcode is going to end up calling execve on bin bash. And so all that does is spawn a shell. So when you call bash like that, that's doing execve on bin bash. So ultimately, you have an exploit that looks kind of like this. Let's see if it works. Maybe, maybe not. Oh, look at that. So if I run ID, then we can see that I have a bunch of different groups. This will actually, ID will work on the lab. but pretty much nothing else will. And as soon as you run a command, it's going to kill itself. But that's an example of a buffer overflow where the non-executable bit is disabled and the stack canary is disabled. So in a case where these two protections are disabled, and you have a stack-based buffer overflow, you can execute arbitrary shellcode. And so that's what this is supposed to be teaching you, is that given some random shellcode in these two conditions, you can execute that shellcode. So hopefully that made some sense and somebody is potentially exploiting that and ideally not hacking my account. Does anyone have any questions regarding that? I know there's kind of a lot at the end there. All right. Thanks for tuning in. Hope you learned something. Don't use gets. And if you have any questions regarding binary exploitation, I'm free to answer them whenever. Hit me up on Discord. Currently trying to write a book on it. That is so slow, but it's happening. Hello. What? Nope, that's it. Join CrowdStrike. We have thousands of internship opportunities available. CrowdStrike gang, we're making money every day. Best EDR on the planet. Stop breaches. Join Overwatch. You can hunt literal nation states. Like, you think North Korea is good? Check out CrowdStrike Overwatch. We'll fuck them up any day. Russia, you name it.